So we're continuing on with section 2.2, rates of change and derivatives. In part 1 of this section, we focused on calculating average rate of change over an interval. And we had two different methods for doing that. Both involved calculating the slope of a secant line. So I have the picture here. So let's say we have a curve or function that represents a curve, and we want to calculate the average rate of change over the interval from x to x plus h. To do that, we can calculate the slope of the line that passes through those 2 points, and we refer to that line as a secant line. Okay, so remember I said there's two different methods. The first method was just using slope formula, so finding the change in y over the change in x, or you could find the difference quotient for that particular function first, which is f of x plus h minus f of x all over h, and then use the difference quotient like a formula for that particular function to calculate the average rate of change for the function over any interval that's within the function's domain. And then we left off asking ourselves, what if we wanted to find the slope of the curve at a particular point? So not over an interval, but at a particular point. Or remember we looked at this suitcase falling out of the airplane example, where we wanted to know how fast the suitcase was traveling at a particular moment in time. And we used average rate of change in order to help us estimate how fast the suitcase was traveling at a particular moment in time. But now we're going to look at how to just do that in a more straightforward manner, which leads us to tangent lines. So I have the picture of the secant line here. The tangent line to a curve at a given point is a straight line that touches the curve at only that given point. So here's the picture of a tangent line. So the tangent line to the curve at the point x comma f of x. And though the tangent line might extend and then eventually cross the curve at other places, it's kind of, if we zoom into that point, the tangent line will only touch the curve at exactly that one point. But it may cross if we were to think about extending the line. So the secant line, and then we have the tangent line. Here's our secant line, here's our tangent line. Now remember in the picture of the secant line, the h represents the length of the interval that you're calculating average rate of change over. So we talked about, for estimating the instantaneous rate of change or the slope of the tangent line, we talked about thinking about making h smaller and smaller and smaller. So like think about pulling this point in closer and closer and closer to the point x comma f of x. Right, so pulling that point along the curve so the interval is getting smaller and smaller and smaller. So the slope of the tangent line uses the difference quotient, because remember, slope of the secant line, we could use the difference quotient to calculate. So slope of the tangent line, we're going to think about taking the limit as h approaches 0, so making that interval smaller and smaller and smaller of the difference quotient. Oops. So the slope of a curve at a point is exactly the slope of the tangent line to the curve at that point, and this is also called instantaneous rate of change. So the slope of the tangent line is equal to the instantaneous rate of change which is the rate of change at a point. So to find the slope of the tangent line at an x value, so at a point, you're going to find something called the derivative. And then the slope of the tangent line at that point is going to be the derivative evaluated at a, so at that x coordinate. So the derivative, and this is read as f, it's using function notation, but it's read as f prime of x. So the derivative name, the function's name is f prime. Or if the original function was like h of x, then we would have, the derivative would be h prime, or h prime of x. Or if the original function were g of x, then the derivative's name would be g prime, or g prime of x. So the derivative is what the slope of the tangent line is equal to. So the derivative is equal to the limit as h approaches 0 of the difference quotient, right? This is just the difference quotient. Okay, so note for an input x equals to a for a given function f of a is the height of the point, and f prime of a is the slope of the curve. So f of a is the output, right, or the y coordinate that goes with x equal to a. So like x comma a comma f of a would lie on the graph of f. F prime would be the slope of the curve at the point, also known as the slope of the tangent line. At a comma f of a. So we're going to use the definition of the derivative to find the derivative of this function. Okay, so f prime of x is going to be equal to the limit as h approaches 0 of the difference quotient for this function. So that's going to be f of x plus h, so 2 times x plus h squared plus 3, that's f of x plus h, minus f of x all over h. So notice that if we were to try direct substitution and substitute 0 in for our h's, do you see that we would end up with 0 over 0 in determinant form? So remember how in the first part of this section, I had you guys simplifying the difference quotient, and your goal was to get this h to cancel. And that we used a lot of the same algebra strategies that we did when we were evaluating limits, and we ran into 0 over 0, that indeterminate form. So we're going to do the same here. So for this particular difference quotient, it looks like we're going to have to use the sledgehammer method, meaning that we need to multiply everything in the numerator out to see what cancels. So remember, I have to multiply out x plus h times x plus h. That's going to be x squared plus 2xh plus h squared. I'm going to distribute that negative to have minus 2x squared minus 3 all over the h. This is a limit, so I'm keeping the limit notation until I'm able to use direct substitution again. Distribute the 2 in. So we'll have 2x squared plus 4xh plus 2h squared plus 3 minus 2x squared minus 3. And now let's see what cancels. So the 2x squareds will cancel, the 3's will cancel. And if I factor out an h in the numerator, it will cancel with that h in the denominator, which remember, that's our goal for the difference quotient. So then we're left with the limit as h approaches 0 of 4x plus 2h. And our last step, which I'm running out of room for, is to now try direct substitution again. So 4x plus 2 times 0, right? We're replacing h with 0. Just simplifies to be 4x. And I ran out of room, but ideally I would have shown all vertical steps with my equal signs lined up on the left here. So f prime, the derivative of the function 2x squared plus 3, is equal to 4x. So this is now a formula to calculate the slope of the tangent line at any point in the domain of x, f of x. So for example, let's say that I wanted to find the slope of the tangent line at x equals to 2. I would evaluate f prime at 2 and get 8. So 8 would be the slope of the tangent line at x equals to 2 for this particular function. Okay, so let's find the derivative for this function. So f prime is equal to the limit as h approaches 0 of the difference quotient. So that'll be 1 over x plus h plus 1 minus 1 over x plus 1 all over h. And again, notice if you were, and this will happen every time, if you were to try direct substitution, you'd end up with 0 over 0. So we need to use our algebra to try and get this h to cancel. So we have complex fractions. Let's use LCM over LCM. So I'm going to multiply by x plus h plus 1 times x plus 1 over itself, which I'm allowed to do because it's the same as multiplying by version of 1. When we distribute to the first fraction in the numerator, the x plus h plus 1 will cancel. And we'll be left with x plus 1. And then when we distribute to the second fraction, the x plus 1s will cancel and we'll be left with minus the quantity x plus h plus 1. Make sure you use your parentheses. And the denominator can stay in factored form since we're trying to get that h to cancel. Then distribute the negative so we can get rid of the parentheses and combine like terms. And we can see that the x's will cancel, the 1s will cancel. And you could maybe do this in less steps, but I just want to show canceling the h's in the numerator and denominator as a separate step. But I would have been okay if you did that all in the previous step. Okay, so now we can see that this h will cancel with this h, which leaves us with the limit as h approaches 0 of -1 over x plus h plus 1 times x plus 1. And again, running out of room. So using direct substitution, we'll have -1 over x plus 0 plus 1 times x plus 1, which this simplifies to be -1 over x plus 1 squared. So f prime is equal to -1 over the quantity x plus 1 squared. That's the derivative of the function 1 over x plus 1. Okay, so let's find f prime for the square root of 2x plus 1. So we take the limit as h approaches 0 of our difference quotient, so that'll be the square root of 2 times x plus h plus 1 minus f of x all over h. And again, we're trying to get that h in the denominator to cancel, so we're going to use our ratcon this time. So we'll multiply by the conjugate of the numerator, because we're going to try and rationalize the numerator by multiplying by the square root of, that'll be 2x plus 2h plus 1. And I get that just from distributing the 2 here. Plus the square root of 2x plus 1 over itself. So we have the limit as h approaches 0. When we distribute, okay, that'll be 2x plus 2h plus 1. And then when we distribute here, that's going to end up canceling with, when we distribute the square root of 2x plus 1 to the square root of 2xh plus 2x, sorry, the square root of 2x plus 2h plus 1. Those will cancel. And then it'll be minus the quantity 2x plus 1. All over h. Leave the h factored out of the denominator because we want that h to be able to cancel. And then distributing and combining like terms, we will be left with, it looks like we'll just be left with 2h in the numerator. The 2x's will cancel and the 1 will cancel. So now we get the h in the denominator to cancel with the h in the numerator. And we will be left with 2 over the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. So now we're ready for direct substitution. I'm going to come up here. We'll have 2 over the square root. I'm dropping the limit because I'm substituting 0 in for h. So that leaves us with 2 over 2 times the square root of 2x plus 1. But we see we can simplify that further. The 2's will cancel. So the derivative is just going to be 1 over the square root of 2x plus 1. So this is f prime. So these last 3 examples were just practice finding the derivatives of these 3 functions using the limit definition of the derivative. We're going to do the same thing for this function, but then we're going to actually use it. So f prime will be equal to the limit as h approaches 0 of the difference quotient. So negative x plus h squared plus 6 times x plus h minus 3 minus the original function f of x all over h. We have to use sledgehammer, just multiply out everything out and simplify or combine like terms. So this is also good algebra practice. All right, and the best part, seeing what cancels. Notice that we're left with only terms that have an h in them in the numerator, so we can factor an h out in the numerator. So this h cancels with the h in the denominator. Which now when we use direct substitution, you're just left with negative 2x plus 6. So this is our derivative, negative 2x plus 6. That is f prime. All right, the second question here is what is f prime of 4? So that's just evaluating the derivative at 4. So we end up with negative 2. Well, negative 2 is going to be the slope of the tangent line at x equals to 4 for this function, meaning it's the instantaneous rate of change at x equals to 4. So that means we know that as x is getting larger, so going to the right from x equals to 4, the function values are going to be getting smaller since the slope of the tangent line at that point is a negative. So part C asks for the equation of the tangent line to the graph of f of x at the point 4 comma f of 4. So first of all, we need to know what f of 4 is so that we know that point. Right now we have the slope of the tangent line at that point, right? This is the slope of the tangent line at that point. And then once we have a slope and a point, we can write the equation of the tangent line in point slope form. Okay, so f of 4, looking back at the original function, it looks like f of 4 is going to be negative 16 plus 24 minus 3, which is positive 5. So the point that we calculated the slope of the tangent line to is the point 4 comma 5. And then the slope of the tangent line is negative 2. So putting that information together, y minus 5, I'm using point slope form, y minus 5 equals to the slope times x minus 4. So this would be the equation of the tangent line to the point 4 comma 5 on the graph of f. And if we were to, let's look at Desmos for a second. So if we were to type in y equals negative x squared plus 6x minus 3, and I believe this will let me type in, I could always add 5 to each side to do y equals, but I believe this will let me type in the equation in point slope form. Your calculator would not, you would need to solve for y. So we can see, if we zoom in, will that let me zoom in? If we zoom in enough, doesn't it look like the line, the blue line, kind of merges with the graph? So at the point 4 comma 5, the tangent line ends up looking like, if we're zooming in farther and farther and farther, it looks like the line is merging with the graph of f of x, which is why we are able to say that the slope of the tangent line to the curve at that point tells us the instantaneous rate of change at that point, or the slope of the function at that point. How y is changing with respect to x at that point. Kind of cool. Okay. So let's say we wanted to find the equation of the tangent line to the graph of x squared at the point 2 comma 4. So we have the point. We need a slope to write the equation of the tangent line, meaning we need the derivative. So let's find f prime by taking the limit as h approaches 0 of x plus h squared minus x squared all over h. Multiplying that out. Looking at what cancels. And seeing that we could factor an h out of the numerator. So that the h in the numerator cancels with the h in the denominator. And then we can use direct substitution, and when we use direct substitution, we're just left with 2x. So the slope of the tangent line at the point 2, 4 is going to be the derivative evaluated at 2, which is 4. So now we have a point and we have a slope. So y minus 4 equals to 4 times x minus 2. Which if you wanted to change that to be in slope-intercept form, you could. Okay, so either point slope form or slope-intercept form is fine. That's the equation of the tangent line at 2, 4. So instead of graphing by hand, which you could, well, let's graph by hand for fun. So I'm going to graph x squared first. And then from point slope form, right, the point is 2, 4. And there's a slope of 4. So in purple I have the tangent line. So you could see if we zoom in, if we did this on Desmos, it would show this even better. If we were to zoom in at that point, it's like the tangent line and the function merged together, meaning that the slope of the tangent line gives us the rate of change for this function at that point. Okay, and we can do it again. So again, using the limit definition, so taking the limit as h approaches 0 of the difference quotient, using proper notation, looking at what cancels. Oh, and then also how about in the numerator that an h can be factored out? So that those h's cancel. Oh my goodness, we again end up with 2x as the derivative. Now, if you, for whatever reason, have already studied some calculus, you may already know some of the shortcuts for finding derivatives. On this test, you have to show using the limit definition. I am expecting you to know how to use the limit definition to find the derivative. So you may not use any shortcuts prior to this test or on the test. Okay, so we want to find the equation of the tangent line at the point 1, 3. So we need the slope of the tangent line there, which will be f prime of 1. Okay, which is equal to 2. And then using point slope form, y minus 3 equals to 2 times x minus 1. This would be our equation of the tangent line at 1, 3. we don't need to graph. If you want to graph it on Desmos to check it out and make sure that that makes sense, then you can. Okay, so let's look at a word problem. So an arrow is shot into the air and its height in feet after t seconds is given by the function negative f of t equals to negative 16t squared plus 80t. So for this function, based on plugging in different times in seconds, you could determine how high off of the ground the arrow is. If we wanted to sketch the graph here, why don't we factor this? So we can actually factor out negative 16t, that's the GCF, and then we'll be left with t minus times t minus 5. So we can see that the solutions to the equation negative 16t times t minus 5 would be t equals to 0 and t equals to positive 5. Those correspond to our x-intercepts, or our t-intercepts in this case. Okay, since our independent variable is t and time is in seconds, and the dependent variable, or the f of t represents the outputs, right? Height in feet. So 0, 0, and then 5, 0 are intercepts here. So I'm going to go 1, 2, 3, 4, 5. And then hopefully you guys remember that that means that the axis of symmetry would have to be halfway between those 2 points. And the vertex lies on the axis of symmetry. So we know that the vertex would be at 2.5 comma something, and you could find out what that something is, which would be the height of the arrow at 2.5 seconds, which when we plug in 2.5, running out of room, I get 100. So the vertex, go by tens, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So this graph models the path of the arrow. So you can see the arrow is shot into the air, and it goes up, 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 before it goes down, 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 back to the ground. So question A asks, find the height of the arrow when t equals to 3. So that's just going to be finding f of 3. And we end up with 96 feet for that. So that would be around here. Right, that would be the point 3 comma 96, which is maybe does not look that accurate on my sketch, but 3 comma 96 is a point on the graph. It represents the height of the arrow after 3 seconds. If we wanted to find the velocity of the arrow when t is equal to 3, so how fast the arrow is moving when t equals to 3 seconds, we want to find basically the slope of the tangent line at t equals to 3. So we need the derivative to do that. So the derivative will be f prime of t equals to the limit as h approaches 0 of negative 16. I'm using t's instead of h. Okay, and then we multiply that out in the numerator. All right, the fun part, you get to see what cancels. Notice we can factor an h out of the numerator. Those h's will cancel. And when we substitute 0 in, we'll get negative 32t plus 80. So the velocity at t equals to 3 seconds will be f prime of 3, which is negative 16 feet per second. Okay, so the slope of the tangent line at 3 seconds is going to be negative 16, and the units are feet per second. So like if we wanted to come up with the equation of the tangent line at that point, at 3,96, that would be f of t, I'm using f of t instead of y, minus 96 equals negative 16 times t minus 3. So like that would be the equation of the tangent line at that point. So if we want to find the time it takes the arrow to reach its peak, since you guys have studied quadratics, you know that the vertex is going to be the location of the maximum value for this function. So we can see it takes 2.5 seconds for the arrow to reach its max height. But let's look at it from a calculus perspective. So the slopes of the tangent lines correspond to the velocity of the arrow. So we've determined that at t equals to 3 seconds, the tangent line had a slope of negative 16. That means as time is passing, like going past t equals to 3 seconds to 4 seconds, that the height of the arrow is actually decreasing at a rate of 16 feet per second. So the negative slope of the tangent line means that y is decreasing. The function values are decreasing at that moment in time. So we can see that the arrow goes up, 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 and we would have positive sloping tangent lines at these points to the left of t equals to 2.5, meaning that the height of the arrow is increasing as time is passing. And then it reaches this maximum height of 100 feet, and then it starts going back down. Well, there would actually, so if we evaluate f prime at 2.5, notice we get 0 feet per second. And that's because the arrow goes up, 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 and then it kind of hangs in the air for a second before going down, down, down. So we're actually able to, from a calculus perspective, determine when the arrow reaches its peak by solving for when the velocity, so when f prime of t would be equal to 0. And when we do that, we get t equals to 2.5 seconds. So that's just determining when the arrow reaches its peak from more of a calculus perspective. Okay, so we will talk about this a little bit more in class.